Now we are going to discuss the last topic of this chapter, which is about the first law of thermodynamics. We have seen its application for the closed closed systems, right? Closed systems means where we have fixed mass, and remember that we haven't talked about the application of first law of thermodynamics on open systems yet. Okay, so that's a topic which would be discussed I think after your first sectional exam. So my question is, we would discuss few more applications of this first law of thermodynamics. Few more means I think only one, which is about the cycles, thermodynamic cycles. And then we would leave this topic at this place. We would discuss the application of first law of thermodynamics for open systems later on. Okay, I think after your first section. So let's talk about the exact topic which I have. That is the energy analysis of cycles. And once we talk about cycles, we are concerned with thermodynamic cycles. And what do you mean by a cycle? Just remember that PV diagram. That was pressure and this is volume. You have two states. Let's say this one and this one. This is state 1. This is state 2. And by some process you go from this state to this state. Now cycle means you come back to your original state. Okay, that's what you mean by a cycle. This is a process. By the way, this curve is representing a process. And what process of that? What is the name of that process? Generally these are basically what? Polytropic processes, because they are represented by which curve? PV raised to power n equals constant. So if somehow or the other you go back to this state, this is something which is the representation of a thermodynamic cycle. Okay, so let me write down the definition. A thermodynamic cycle is a sequence of processes. I hope you understand what does that mean, sequence of processes. I mean, this is one process and this is the other one, so they are going sequentially, right? Not in parallel, they are going sequentially. One completes and then you go for the other one. So a thermodynamic cycle is a sequence of processes that begins and ends at the same state. Okay, now it means at the conclusion of that cycle, I mean, what does that mean? At the conclusion, this is the starting point and this is the concluding point as well, right? Why? Because it has gone to state 1 to state 2 from 1 and then it comes back to state 1. So at conclusion of that cycle you are again on the same state. Now can you please tell me what would be the difference in the energy overall? What would be the change in energy? That should be, no, I am not talking about work, I am talking about energy. Just look at that. Obviously the system would have some energy content at that place, some energy content at that place. If you look at the overall energy change, the system has gone from state 1 to again state 1. So it means it has reached the level of energy which it was having at state 1, right? So what was the total change? It's 0. So you can say that over the cycle the system experiences no net change. Not only energy but also state. Now, by the way, why we just look at the application of those cycles. If you look at the functionality of an automobile engine, I mean it repeats its processes. Okay, the valves open and then they are closed. The piston undergoes an oscillatory motion. Okay, so that is in itself it's a thermodynamic cycle. Similarly, you would see the applications of those thermodynamic cycles in refrigeration. Okay, you can see that refrigerant is flowing inside those tubes. It is accumulating heat out of whatever is there in your refrigerator. And similarly, those air conditioners. So they are undergoing certain thermodynamic cycles. Similarly, you can look at the application of jet engines as well, right? And the power plants. So the application spectra is huge. Okay, so the point is, where for what kind of application, what kind of cycle do you use? So what we are going to discuss is that we have two major types of thermodynamic cycles, and those cycles are basically known as power cycles, and this is basically dependent on the utility. Okay, utility of those cycles, application of those cycles. And the other one is, you can say, refrigeration / heat pump cycle. Now, although their fundamental functionality is the same in this case, refrigeration and heat pump, but originally their application is different, right? How do you see the same thermodynamic cycle in different perspectives? Okay, so that I would tell you, but the major difference is this one. One is power cycles and the other one is refrigeration heat pump cycle. Now, let me explain power cycle first. You might have seen that in your elementary course on physics, you have a hot body, then you have your system, which is demarked by a control surface, and then you have cold body. For example, if you look at your engine, let's say, just look at the engine, automotive engine. Somehow or the other, you are producing some kind of energy which can be converted into heat. That is due to the combustion which is going on inside the engine. Okay, and that system is taking that heat in the form of energy. Basically, it is obviously the heat is a form of energy. It takes that heat, it does some work out of it, and you can say sends some energy out in the atmosphere. So you can say that heat coming in the system is, some portion is going out as work done by the system, and some heat is being sent out to the cold body. And what is the cold body in that case? If you are talking about the engine, the atmosphere is the cold body, right? Because due to the combustion, temperatures are very high as compared to the atmosphere. So obviously, if you just compare the temperatures, temperature of the combustion chamber would be very high, temperature of the atmosphere would be very low. So atmosphere would be treated as a cold body, and that combustion chamber would be treated as a hot body. So it would take heat from the hot body, it would do some work from that energy, and then it would send some energy out in the atmosphere. This is something which is, you can say, a very fundamental representation for power cycle. Temperature what?
So the hot body and the cold body is atmosphere.
Okay.
Kind of
No, I'm not talking about inside the cabin, the passenger cabin of the car. I'm talking about the combustion chamber inside the engine. Now the temperatures are very high, almost thousands or hundreds, you can say, degree of. So that's the point. So from hot body, and similarly you also do this kind of thing in your power plants. Okay, you extract heat from the steam, and that steam is again, you can say, heated by some other means. You extract heat, you run your turbines, and some of the energy is sent out in the atmosphere. Okay, so this is something which is the power cycle. Now if you look at the first law of thermodynamics, what was that law? That law says, because we are talking about a cycle, so let me put that in the subscript, we are talking about the overall cycle. Now what is that change for a cycle? That is 0 for a thermodynamic cycle. So it means Q cycle minus W cycle would be 0. So that is the equation. That is the fundamental equation for this power cycle, power thermodynamic cycle. Okay, we would use that equation to look at different aspects. Now what that Q cycle is, this would be the difference between what? Yes, obviously, I mean if you look at Q cycle, so hot body is giving heat to the system, so I can say that I would put that equal to what? With a positive sign or with a negative sign? If the heat is given to the system with a positive sign, so I would say that this is Q out minus, sorry, this is Q in, because that is something which is Q in, this is coming inside the system, and that is something which is Q out. So, and because the work done by the system is positive, so I would keep that negative sign on, and that would be equal to what? Right? Or you can say that it would be equal to Q in minus Q out equals W cycle. So it means what is the difference in those energy levels? That would be exactly equal to the work done by the system. Okay, and for example, if you look at the work done by the automotive engine for a car, so that is what it is driving, right? So it is driving the car. That's what the work is done by the engine. So you can say this is how you represent those power cycles. Now how to look at, I would describe their performance coefficients as well, but let me complete that refrigeration or heat pump cycle. Oh, I'm sorry, this is heat pump cycle. In that case, now what can you see? For example, just look at the functionality of a refrigerator. From a very common point of view, you can see that the temperature of the refrigerator is, let's say, obviously it is lesser than the atmosphere. Still you are trying to extract heat from that colder body, and you are trying to extract it in the hot body. Do you understand what I mean? Just look at the temperature of inside your refrigerator. Obviously it is much lesser than that of your atmosphere, right? So still you are trying to extract that energy from the refrigerator, and you are trying to send it in the atmosphere. So it means energy is taken from the cold body, and energy is being sent into hot body, right? And for that matter, because you are going in the reverse direction, you are basically reversing the cycle. I mean, you are taking the heat away from a lower temperature body and sending it to the higher temperature body. So obviously you need to do some kind of work on it, right? So instead of getting work from that refrigerator, you are going to do some kind of work on that. And how do you do that work? By providing electricity. Okay, by providing electricity, you try to run those motors or whatever that pump is, and then you try to extract heat from that body and send it into the hot body. So how do you represent that? This could be a hot body, which is basically the atmosphere, and then you have system which could be your refrigerator, and then you have cold body. So you can say that you are extracting heat from this side, which is Q in, and you are doing some kind of work on the system, work done on the system, okay, and then as a result you send some kind of heat in the towards the hot body, okay. So that's the difference. Any question about that? What would be the cold body in case of that is the cabin of the refrigerator. If you look at the cabin of the refrigerator, obviously its temperature is lesser than, much lesser than the temperature of the hot body, which is the atmosphere itself. No, I mean this refrigerator is something which is representing that refrigerant flowing inside or outside. Do you understand that? Obviously it would extract that energy by flowing inside the tubes which are there inside on the walls of the refrigerator. It extracts energy from whatever the food you have placed in your refrigerator, and then it sends out it into the atmosphere, okay. The refrigerator what? You tell me. Why? You tell me. Now, for example, just to give you a very, you can say, it's my first response on that question. Just look at that. How do you extract heat from that refrigerant so that it can be sent out of the atmosphere? Just look at that. You try to keep the backside of your refrigerator with some space from the wall, with some gap from the wall, isn't it? Why do you do it? So that you can have proper convection from those walls. Or the second mode would be for that heat transfer is radiation. Now if you put that into that vacuum, what do you think? Which heat transfer mechanism would be missing? So obviously that would be very less. So it would affect the performance. I mean, you should look at all these things from a very fundamental point of view. Okay, so that's my objective. So the point is, no, you have to keep it moving. You have to keep that refrigerant moving, right? And to keep that flowing inside those tubes, what you need to do? You have to provide it some kind of energy. And how that energy is being given to it? By providing some kind of electricity to the compressor. And that compressor is basically trying to keep that fluid moving inside those tubes. Did I answer your question? So ask it again. To the refrigerant, yes.
So how is that happening? Is the refrigerant colder than the cold body?
How can it be? I mean, how can it be? If you want your heat extracted from the cold body, which is at, let's say, temperature T1, and it is going to your refrigerator, so which temperature should be high? The cold body. That's how heat would be flowing from the higher temperature to the lower temperature, right? You can't violate those principles. I mean, you can't let the heat flow from the lower temperature to the higher temperature. You can't do it. Okay, so obviously you have to design that mechanism. You have to keep that refrigerant cold enough so that heat would flow from the refrigerator to the refrigerator cabin to the refrigerant. Okay, so let's talk about the performance. I mean, you can write down what those equations are. How come? Okay, just keep that door open. So in northern areas, do you want to keep your food inside the? I mean, have you looked at any movie where you have been watching those things on Siachen, or let's say like that? So you tell me. I have given you the basic sense. You tell me. Is it possible? By the way, do you need a refrigerator there? Tell me. Do you need a refrigerator there? You have so much snow outside. Why do you need a refrigerator? No, that's what I am telling you. If you are putting those two bodies at the same temperature, now what's the advantage then? Just keep your food inside the atmosphere. I mean, is there any need of refrigerator? If there is no need of refrigerator, you can have the same temperature which you can achieve in the atmosphere, which you can achieve by using a refrigerator. So why do you want to spend like 35,000 or 40,000 rupees on a refrigerator? Is there any objective of having that? I mean, do you want a heater in the summer season? Let's say if you are in Multan or even in Islamabad, do you want that heater? Not at all, right? So that's the point, that everything is defined with some certain objective. If the objective is not there, you can't define the need or the requirement of that system. Then these are just numbers. I mean, okay, these two things are zero, everything is zero, you don't have to do any kind of work. That's what it is, isn't it? Just look at that. If those two things are equal, Q dot out or Q dot in, or let's say they have the same temperature, if it is zero, so work done required would be, these are just numbers. Okay. So just look at that. How do we define the performance? Okay. Performance of the power cycle. That performance is defined as thermal efficiency that is basically eta equals work done by the system divided by Q in. I mean, how much of energy has been converted into work done, right, divided by the total energy supplied to the system. So this W cycle can be written as Q in minus Q out divided by Q in. So if you look at that, that would be equal to 1 minus Q out over Q in. So eta will only be less than equal to 1. That's what it is. I mean, you can always convert some portion of energy, not the whole energy, into work. This is against first law of thermodynamics. If you claim that you are going to convert all the energy into work, this is against first law of thermodynamics. This can't happen. Similarly, let me talk about performance of refrigeration or heat pump cycle. So, by the way, what is the difference between the refrigeration and heat pump cycle? This is only a difference in perspective. For example, if you talk about refrigeration, you don't want to let your temperature go below a certain range, or higher than a certain range. For example, if you set your temperature at 0 degrees centigrade of the refrigerator, you don't want it to go above 0 degrees centigrade, right? Similarly, if you talk about heater, it's kind of a heat pump. Just look at the functionality of an electric heater, and you set that temperature at 25 degrees centigrade. So you don't want to let that temperature go below 25 degrees centigrade. So that is just the perspective. In one case, you don't try to keep the temperature higher than a certain value, and in the other case, you don't try to keep that temperature lower than a certain value. So that is just the difference. Otherwise, its fundamental functionality remains the same, which I have already described. So in that case, how do you define that? For refrigeration cycle, obviously just because of that perspective, we have two performance coefficients for these. Functionality remains the same. First law of thermodynamics remains the same, the form, but the performance coefficient changes. So for refrigeration cycle, we have performance coefficient named as beta, and that is written as Q in over W cycle. And for that matter, you can say this Q in divided by Q out minus Q in. So that is something which would define the performance coefficient for refrigeration cycle. This is basically performance coefficient. And you just do one change in this definition for heat pump cycle. For heat pump cycle, you say that gamma, which is the performance coefficient, that is written as Q out over W cycle. So that is the only difference, and that is due to the perspective which I have already told you, that in one case you don't want to go let your temperature go beyond a certain range, and then in the second case go below a certain range. So this Q out over Q out minus Q in, this is how you define gamma. Okay, and generally in both of those cases, tell me which one is higher, Q in or W cycle? Which one is higher? Okay, just look at that. In the previous case, you cannot achieve thermal efficiency greater than 1. In this case, tell me, can it be greater than 1? Come on, think about it. And again, there is a small point just to understand that. By the way, you want to have the maximum values for gamma and beta, and generally they are kept at greater than 1. Just look at that, their comparable values, and try to understand that. Okay, I have given you the answer. I have told you the fundamental concept. I have also discussed the application. Okay, so please just look at that and see what range is possible, and go back and try to search on Google what is the performance coefficient for the commonly found refrigerators. Just see those values, okay, and try to find out what is the thermal efficiency of an automotive engine. You would see that it won't be greater than like 30-40%. You would see that. So whatever energy you are trying to have from your combustion, 60% or 50% of energy is wasted inside the atmosphere. It is lost. Abdul Rahman, you have a question? Done? Okay. Right? So that's what I need to discuss about these things. We are done with chapter 2. So I would start chapter 3, which is about the PVT diagram and all the phases related to thermodynamic substances. Thank you.